Then I'm sharing this attack. Okay, so we'll start in activity. Yeah, that's good. But let me admit myself.
Recording in progress.
I don't actually.
Leave.
Yeah. Five.
Morning.
No, but no.
It is the new generation, they're not like going to class physically.
See, people that do not come to doctor.
Yeah, I don't understand. I don't know what type of generation.
Well, we might get, we got John, who's no longer here, this is what we're going to do. And we got Jack, you,
Yeah,
we might get more people.
but you have to watch it or you have to catch it up anyway, so I don't.
But there are some people who are taking, say, classes, at the same time, candidates, so,
I'll take calculus.
yeah, this week, next week, they can't come at all, so they go recording.
I see, oh, yeah, because there are, okay, I have only one summer class.
And then there are some people in either not in Bloomington or not in India or not in the US.
It's a different generation, it's definitely different than growing up. I was in a class last semester with 400 people, 120 people or so. And in the first two lectures, the room was full. And after that, nearly nobody there to know, but
So every semester since after the pandemic, I started with saying by this class is gonna be in person, and then. There's somebody saying I'm sick, so I say, well, I guess just for that one person, I have to offer the hybrid thing.
yeah,
But my classes are in the morning, they end up not coming, and I understand sometimes it rains, sometimes they're tired.
it's just different way how they do it. But
They would have done it differently, say, 5 years ago. So it's not just a generation, it's just
it's
the
not,
time.
yeah,
And the thing, so now it's 8:45, I don't know if people can hear me, so I'm going to check with Ahmad, for example. Ahmad, can you say a few words, please?
Yeah, I can hear you.
Very good. All right, now for the other people living in us, my typical question is, which question should I ask? All right. Okay, so what has, the idea was, can you hear me? So that's the thing. So I'm gonna say the question. And if you guys can hear me, write down the answer. If you do not know the answer, that's totally fine. Write the question. At least you will confirm that you've heard my question. So just to make sure that everybody online now can hear me, my question is, what has two butts and can kill you? I don't think we asked this question this semester yet. What has two butts and can kill you? So you either know the answer, and you write the answer, or you write a question if you don't know the answer. If you can't hear me, then you don't say anything, then I'll be worried. I know at least Ahmad can hear me. What has two butts and can kill you? Let's say, Anissa, what do you think? What has two butts and can kill you? What has two butts and can kill you? That is correct. And here's the answer. What do you think? It's just a joke. This is true, an assassin can kill you, right? All right, good. So we heard from Carla and Alyssa and Ahmed, and there's nobody else because there's me, Ahmed, Marcia. Very good. We're gonna start. So if you have any questions or anything that you would like to do, since you see that the chat is working, go ahead and write in the chat. I'm gonna close the chat, but as soon as somebody says something in the chat, I get a notification. So I'm gonna close this. And then I have the participant, that's 5, that's me, with me. And then Ahmad Ali San. Then I'm gonna close this and I'm good to go. So I'm gonna minimize this here and then I'm sharing the screen. And I'm gonna stop sharing a little bit and I'm gonna say, let me just show you this thing. So you know what I mean when I move things on the screen that you guys online cannot see. For example, if I go to participants, so look on the screen behind me. Do you see how this thing moves on the screen? Right, so we see it here and sometimes it bothers us, right? But you guys online don't see it and I have to deal with them. So for example, if I were to press escape, I think the controls will show up. I think it'll, well, no, don't show up because I'm not sharing. So bottom line is that I might do things with the mouse that you may not understand why online. Now I'm gonna start sharing again. Wait a minute, something. Come on, let me read that, but that's good. So in the chat I have, okay, I have Ahmad. I will close it, it's annoying, I agree with you. And and I will close it right now. So I have the other Ahmad online. And then we have Shivam is here. Look, you were complaining, so you don't, all of a sudden, we got an approval here, John, 100%.
Yeah.
For
Yeah.
now. So we also have Shivam. And we're gonna get started with the controls here on the Windows that I am on. I can just type Control Shift H, I guess, Control Alt Shift H, and then I go the way. So absolutely, I'm gonna close this guy.
I was not complaining, I was just.
Just pretending that.
Just saying what I did, what I realized.
Yeah, sorry for using the.
Yeah.
As you were saying, what you realized, there is an improvement of 100% in attendance all of a sudden. So I'm sharing. I hope I'm sharing correctly. And then I'm going to say, what am I going to say? This guy, which again you don't see. Control Alt Shift H. I don't need it, although later I will need it. So if anybody writes something in the chat, then I can see it. If anybody says something, I will definitely see it, unless your audio is not good. And say for now, so let's just get started. So I'm gonna go and say that I'm logged in. And I'm gonna go to the website for this class. We have okay, yeah, sorry, I'm gonna type the few characters that I need to get there. I click here and I'm going to say, these are the dates. We are on the 21st. If I click on the 21st, I say today we should start talking about the mystic state formalism. But just to prove that we understand what's going on, we should prove this diagram. So this diagram has to be read as follows. If we knew what 0 is, and if we knew what 1 is, and I'll tell you now, and we'll go over this slower, they are actually values of qubits. So they are either one state or another. But anyway, they really look very much like the classical states. 0 and 1, if you take a coin and you look at the two sides of the coin. X is the first gate that the book introduces, and it's called a NOT gate. And so, because I have a line between 0 and 1, I'm going to say that X with an input of 0 will produce 1, and X with an input of 1 will produce 0. So that line goes both ways. So I would like to be clear, eventually by the end of the lecture today, where we first introduce this thing. Shivam, I gave you a book or not? Did I give you a book like this?
No.
Well, I'll give you a book, as long as you stay in the course.
Yeah.
We have a lot of flux going in, out. I have one student who signed up 3 times and dropped 3 times. And then you sign up twice and you drop
Yeah,
twice.
this is my second time, yeah. So because the first time I wasn't sure about the financial data again, so I would.
Great, so right now, we're back at 10 students, I think, but then one ad is still pending. And this is a student visiting the campus from the call. So whether he will make it to class today or not, he said he would try it out anyway. Then whoever comes to class, I can give you a hard copy of the cues for quantum. And that's what we're gonna start with now.
I have a question. Can you have because yesterday we had this 3 axis, right?
Yeah.
Can we have a knot on the right left axis?
So you can apply it not on anything. But to start with, not doesn't make any sense unless you take 0 and you make it 1 and take 1 and make it 0. But 0 and 1 are not true and false. They are the things that we discussed yesterday. So we have to understand that eventually we need to accept and be able to work with the fact that every qubit is a vector. What kind of vector? It's a unit vector in a sphere that has radius 1. So I'll show you the sphere in a second. We have the you want to come in? You want to watch from there? How are you? I'm good. How you doing? So when we talked yesterday? Did we talk yesterday?
Yeah, we spoke over you.
So your name is Ashish?
Yeah.
And what's the P in front?
Oh, it's Pretorian, it's my last name.
Last name, so we don't worry about that, we want to, okay. So then, I think I process you a E-add, now are you gonna stay in the class?
Yeah.
Pretty good, it's a book for you,
Sure.
and well, I'll tell you more about it, this is basically right now, this is a textbook, right away. So, we have 3 people. In the room, we have about the same number of people online, and then that's synchronously, right? And then we also have people watching the recordings and doing stuff. I'll prove to you that people watch the recordings. In fact, I'll explain to you that what the purpose is, for example, for a grade. How do you get a grade in this class? And then there's 10 people who don't get a grade, but they have to sort of justify their status as a focus group. And I still have to meet with them as if giving them a grade, basically, because they basically report back with feedback on what they think about this. So we'll talk about that later, but it's not that important right now. So I have this diagram, and I say this is what's happening between X. So when you apply X, which is a NOT gate, if you want to discuss transitions between the 0 and the 1 state. So in our classical world, 0 is false usually, and 1 is true. That doesn't work over here because, as I said before, qubits are vectors. But what other things do we have over here? We have a second type of gate, H, which in the book is called Pete. It's called Pete because of Pete Shackleford, which is listed. Where's Pete? Oh, I don't have Pete over here. Oh, darn. I will show you slides with Pete later. And also the story of how Pete came to be the one who gave the name of the Hadamard gate in this book. So
the qubit is a unit vector in which vector space?
So it's a two-dimensional.
Okay, two-dimensional.
However, two-dimensional as it is, the coefficients are complex, which means another 2 dimension for each one of the 2 components.
Yeah.
So what we are going to do is remind you that yesterday we had a lecture. By the nature of that lecture, you basically could ask questions, a lot of questions and so on. I'm going to say allow. And then if I go through this, I'll find my right. So this is what we did yesterday, and you can see the sphere. That's called a block sphere. What we'll talk about it in a second. I'll show you how to do it in Python as well. The block plot essentially shows the space where vectors or qubits behave or exist, live.
So you see how 0 here and 1 at the bottom, which is not showing in this particular one, are two possible states. And you should know this about the block sphere right now. It's fine, it's good device for you to visualize things, but it's wrong. So when you're talking about the basis, since the space is two-dimensional, then the basis is going to contain two vectors, and they're supposed to be orthogonal. They also have to be normal. I mean, same orthonormal, that means they share the size 1. Well, no, look at 0 and 1. They are not orthogonal. They have 180 degrees between them. That's the only problem with the block sphere. It distorts the angles. So now, instead of being orthogonal, they are like opposed. So this is a distorted space that only has this one little distortion. We have two more bases, would be for Bloomington, which are going to be plus and minus, and then we have this left and right that we introduced, which goes by other names. We need complex numbers for this basis, right? We need superposition for this one, and then we don't need anything for 0 and 1. So I said yesterday we had a very nice lecture, and the property of that lecture is that you get to hear a lot of things that we have not yet discussed in depth, because that's how they are. And so this lecture, don't expect after the lecture to have understood everything. This is something that we will refer to again and again, several times. I have another thing that I would like to share before we get started is a little bit. I know I keep in this list of what's new, stuff that I would like to share with you. And I don't expect you to necessarily read this, especially June 9. That was well before the course started, right? But then I know I put it there and I can refer to it, so I don't have to look for it. So this is Umesh Vaziraj, and this is not his playlist. I mean, he did a video. Somebody else combined the videos and put them over here. This is an outstanding course, and it's a 100 level class in Berkeley. And in the end, we have to relate to some of these videos by the end of the semester, which is in 5 weeks from Monday. If you scroll down, there are some honestly excellent lectures, but the one that I want to discuss here is this one. Yeah, so that
I feel like I'm dealing with what seems like an ever extreme details. Please help me be way more efficient with times.
Yep.
In this video, we'll talk about the uncertainty principle as it applies to qubits.
So then what I wanted to do in the share here, I'm going to give you some computer sound, let's say super high fidelity, whatever that means, and then make this big. I'm telling you this video exists, and I'm going to go straight to the point of my aim, but we won't watch this video now. For today, you were supposed to watch the video by Terry Rudolph, because that's the formalism that we're supposed to start. That's a formalism that is good for people. People in 6th grade could use it as long as they understand it, as long as they practice and do the exercises. So as you go through this, you're saying, what is the uncertainty principle? It's this thing that if you look, next year, it will be the International Year of Quantum, because of 1925, 2025. And now finally, the whole world is going to celebrate that. So back then, when they came up with the first quantum revolution, second, whatever, the first understanding, the second understanding of it, like 20 years, it was cleaned up and presented much better. They tried to understand things in classical terms, and they couldn't. So then they thought, oh, it's very weird. As John was saying yesterday, it's not weird, it's the way it is. And all we have to do is to adjust our minds to actually understand it in the terms that it presents, because it's a very powerful theory which actually applies everywhere, except for general relativity. Now I'm going to say that that's just that one important difference.
Why?
Otherwise, everything else in physics is explained by quantum mechanics. So,
Are you not general relativity?
oh, the question is very deep, and I don't have an answer. It just doesn't. So listen, we'll come back to that in this class. We're not supposed to talk about physics on account that the discussion will go on forever, and because we're not physicists. So instead, we're going to discuss quantum computation, and through that, get to some elements of quantum physics, so we know the terminology. So they actually don't disagree. They don't agree, period. Okay, so since you want a quote, I am going to let's see if I can go. Yeah,
Um, let me see, okay, yeah, so again, I have this problem, and so this is a issue, I didn't mean to bring this up here, and I don't know whether I have the link, and as a result, then I'm wondering now, and so I finally found it. So this is David Deutsch, and it's one of the people who came up with the concept of quantum computation. He has a number of other things, theories that he's working on, and Maria Viola is just gonna come and have 3 lectures, works with him. I'm gonna click on his picture to get to the transcription of the 6 videos that he posted in 2006. So when you look at, so this was our attempt to turn that video into a document, so people can read the document and have the pictures. There's lots of pictures because it's from a video, right? So they can say, maybe I don't want to watch the video, or I want to watch and focus on a particular part of the video. But look how he starts. Quantum theory and Einstein's general theory of relativity are the 2 great fundamental theories of contemporary physics. Nobody questions that. Between them, they provide the conceptual framework in a mathematical language in which we express all other theories in physics. Okay, why do we need them both? Because they don't agree. They just don't. And now I'm going to go elsewhere. I don't know if you guys know Scott Aronson, but you will find out about him in this class. He is he finished what?
He has a blog, right?
Oh, he has a blog, that's true. He finished his PhD with Umesh Vaisarani in Berkeley, but then he went to MIT. He worked with Grover, very well-known person. I think he's probably 41 now. And I'm going to say that he wrote a book, Quantum Computing Since Democritus, and somewhere in lecture 9, if I could get to lecture 9, he says, okay, I wanted to say that this is from Waterloo. This was taught at the University of Waterloo. They have an Institute of Quantum Computation, and this was, I'm not sure the year, but 2006 also. And Ray Laflamme is a very big Canadian scientist, big in quantum. He finished his PhD with Stephen Hawking. So only big names over here. And this is the discussion at the beginning of the lecture. He says, where does it say operating system? We are here in, see, there you go. It says, basically, that's Scott talking. Quantum mechanics is the operating system. That's like a computer science centric view. It's the operating system that other physical theories run on as application software. Also, it's the foundation at the bottom, right? Great, we should learn. We should not try to learn it as a physicist because there's too much. We should learn quantum computation, and I'll show you later why. Because you will learn some quantum physics, but only as much as you need, at least the terminology. So it says here, because that's what Elmar is asking, well, why is general relativity disagreeing? Well, nobody knows. But his point of view says, think of quantum mechanics as the operating system for the rest of the physics, except general relativity, who hasn't been ported to this system yet. But that's the joke. I mean, you don't port it unless you understand it. But that's the basic idea. You can't reduce general relativity, whatever that may be, to quantum mechanics. Other than that, between the two of them, everything is explained in physics.
Okay, it's going off, but if you now take quantum mechanics and statistical mechanics, do you have as well something like entropy in quantum mechanics and things like that you could apply information theory?
Absolutely, that's quantum information science.
Okay.
Yeah, so when I have lots of books, and in fact, why don't I just show you one another book? The thing is that, like you said, if we start exploring these things the way they come to us, because the questions are interesting, then we are going to just go on forever.
Yeah.
There's something good in that and something really bad about it.
We should focus on
True.
I agree.
But let me tell you that in this, somewhere in here, not in this one, in the other one with the Scott Anderson. So he said something like, quantum computation is really easy if you take all the quantum physics out of it, which we should do. And so every time I say this, the physicists, they know, then the physicists start laughing. Right? I mean, you're taking the very thing that generated this. Yeah, but we shouldn't talk about this. Okay, we should go and say this is computer science. So there's just a bunch of amplitudes and probabilities and they go like that. So somebody wrote this program, fine, let me understand. So as I scroll down, I want to show you a book, because you say, what about information? What about entropy? And I have, where's the thing? David McMahon. So this is a book that I haven't posted yet. This book
as many other books start with is classical information science. So it says information theory, and then from here starts introducing the mathematics of quantum mechanics for the purpose of quantum computation, and then in the end you end up with entropy. Look at this, there's entropy, and then later on it's explaining how it participates, but in this other world of quantum information science. So let's go back from this general background of information and say that when I go here, the uncertainty principle back in 25 was something that Heisenberg, who didn't know much matrix mechanics, I mean, but because he wasn't working with it, so somebody had to help him when he came back to the continent. He actually went to Helgoland, which is an island that had no trees. So he couldn't have like allergies, suffering from allergies. And there's a book by Carlo Roveri called Helgoland, and he'd invented everything we had to invent. And then he came back, showed those Jordan Pascual, and they said, "Oh, that's matrix theory. So let me help you formulate this." But he invented whatever he wanted and needed by himself. And the point here is that in the principle that bears his name, the idea was that you apparently either know where something is, but not how fast it moves, an atomic particle or subatomic particle, or you don't know where it is, and you might know how fast it moves. And that's the uncertainty principle that people think of in general. But Vasiliani says, I hope folks have been, suppose you watch these videos, all right, which we will do at some point.
Sorry, Anthony,
Sure.
you said uncertainty principle.
This is uncertainty principle.
Uncertainty, because yes, okay, yeah, okay.
So,
okay,
Who
yes.
went to the island?
Helgoland, yes, Heisenberg went on that island to work because he didn't stay.
He came up with quantum mechanics without all the matrix.
Not quantum mechanics, matrix. He didn't know how to provide a formalism for what he knew was happening.
Yeah.
And he ended up inventing matrices and working with them. They came back on land, so to speak. This is a very small island that has no trees, and therefore he could breathe. He had allergies. So he came back and spoke to some mathematicians, and they said, "Oh, we can fix this for you." But the fact is that he understood he has to put like matrices. Let's say you don't know anything about matrices. Then what do you see first? Oh, it's a table of numbers, and now you have to multiply the matrices, and then it has a very special rule. And you have to say, why is that rule? So on. So he came up with combinations of terms in describing what he knew as a physicist was the reality. But the mathematician says, oh, this is already working now. We know how to explain it to you, but he didn't care for that. I mean, until he had to, and then he invented whatever he needed. So the uncertainty principle is formulated in terms of what I just described: location and momentum. And we have, if you look through this, this is the basic theory of right here. This is the diagram that sort of explains, as you were telling me, what's a qubit? A qubit is a vector in one space, let's say two-dimensional space. So let's say we give up on complex numbers, we just put real numbers. Well, then in that case, look at 1 and look at 0. 0, if you guys remember, is a vector of two numbers, 1, 0. Why is 1 on top for 0? Because you look at it as a vector, and the first component is the 0th component. And then you put a 1 there. And the second component is the 1th component, first component in a vector. So 1 is 0, 1. And that's why you have this vector with 0 for the x and 1 for the y. So 0 and 1 are supposed to be, first of all, of size 1 and also orthogonal. And then we talked about plus and minus. And in this case, I don't have a sphere, I have a circle. So plus is 45 degrees up and minus is 45 degrees down, because minus is basically a combination of 0 with a minus 1. Let's see how the component on this side would be minus 1. And plus is a combination of 0 and 1. And that's really the effect of the Hadamard gauge. Because we have to start that formalism so you can see what I'm doing. But interesting aspect of Vasiliani over here, it says, I could in fact show you how you
Tired of typing tons of notes during class? There's finally a better way. It's called Otter.
Corresponding state or a vector.
All right, so if you go through these things, I don't know how many ads that we're gonna get, but that's I guess the price we have to pay if we want to watch these videos for free.
To get an ad block, I guess.
I guess I could ad block it. Right now, I'm gonna just say to you this, that yesterday I said that the uncertainty principle could be formulated in how you measure in these two bases. A measure in a base means project. So if you have a vector, any vector here in this circle, then you project it on the 2, 1, and 0 axis. And with a certain probability, which is proportional with the projection, you get into 0 or 1. Like we said yesterday, if you are on the sphere and you are going to measure in the 0-1 basis, and you are in Oxford, which is in the northern hemisphere, then the question is, when I measure you, I will find you at the North Pole or South Pole, period. And you say, but I'm in Oxford right now. So then, okay, you have a bigger chance that I'll find you in the North Pole, but I could also find you at the South Pole. But the point is, if I am checking for that, then that's where I'll find you, even though you are in Oxford. You could be somewhere else, and it will boil down to North or South, like John was saying geographically, so to speak, like yesterday. And then you could say, I don't want that. I want the other basis, like East-West, for example. And again, when you measure, you're either going to be on the east or the west side. Wherever you are, it will boil down to either east or west, with probability of whatever it is, amplitude. So what he says over here is that this formulation over here, that if you define these terms, how accurate can I make the prediction of what the value will be if measured in that base or that base? He ends up with this lower bound. And that's another way of looking at the uncertainty principle. So the video exists, and you need to sort of familiarize yourself, warm up to the idea of vectors. You can't just jump into this video. I just wanted you to know that this is the equivalent formulation of the uncertainty principle, and it's based on the question that you asked yesterday. If I know, in one basis, can I also know in the other basis? And there's a limit. You either accurately predict in one, but not the other, or the other way around. So what's the question now?
The question now, we have 3 axes, so I think 0 dimension kind of.
We have 3 bases, that's right.
3 bases. So why we know that's not 4 bases, or I mean, could we not have bases?
Oh, because now the question is what transformations do we have? And we have 3 matrices from Pauli. So those are the matrices. Okay, now let's see where I'm gonna go.
Maybe we should just do the length lectures and not.
True, but you say why 4? And the answer is the 3. Why 3? Because there are 3 possible transformations that we are going to study. Therefore, there will be 3 different axes. Now you see, you can also go back and say that in the block sphere, why aren't they perpendicular? And they are not, because we can't represent them that way. But think everything is doubled up. So I'm going to go to 21, and I'm going to say I have this thing that I would like to start describing to you in a second. I have to describe the X gate, I have to describe the H gate, I have to describe the Z gate, and that's all for today. And then you say, what is plus? And we'll define plus as the effect of Hadamard gate on the 0 qubit, and then we'll define minus as the effect of Hadamard gate on us. That's the first video that Terry shows you. And he says something interesting at some point that may have the result of the effect of confusing people. There is a phase that goes on the black hole in the H of 1 or H of black. And he says, why is this phase showing up here? I cannot tell you, but nobody else can. And so I want to emphasize that when we start writing this, these are going to be the definitions. So plus and minus are the effect of H applied to 0 and 1 by definition. And then X is switching between 0 and 1. You say, oh, we know that. That's right. Guess what? Z gate, whatever that is the exact equivalent of X, but in a different basis. Just so you know, Z is in fact not, but not for 0, 1. I said to you that we are going to discuss the formalism that Terry is introducing. Okay, let me briefly, I can just go into the syllabus, I can go here. Q is for quantum, and you know where the video is. If you go to the website,
Which are there any other, like other than plus minus H?
you have the third one, right?
Left right.
Left, right, with that includes the complex numbers. So for example, other gates like S, which I cannot introduce right now because I don't want to use the coefficients at all, and of course I don't want to use complex numbers either.
Because I mean, technically that would be infinitely many, like.
Yeah, technically there will be an infinity. Even in the circle that I have drawn, you take the plus minus and you rotate them a little bit, and you get what he calls U and U per. Sure, you could have an infinity of bases, but these are the bases that correspond to the Pauli matrices that we talked about. So we identified 3 that are equally distant from each other, and that's why they look so good on the sphere. We have north-south, east-west, and then we have forward and backwards. All right, so keep this in mind. There are three bases that we're talking about all the time, but yeah, you can switch to any basis. So in this book, this is the video, and you can get the book from here. But if you look into supplementary material, you could find, for example, in this note over here, he has a very short paragraph in which he says, if you guys know quantum mechanics already, and you came here to see what my system is about, well then, in a very few sentences, I'll tell you what it is. And then, are there any limitations? First of all, in principle, no. In reality, you can only use some unitaries, and he describes this. There is one subtlety and so on. Anyway, so nobody's teaching you anything that is different or wrong simply because it's more acute than the real one. It's a real thing, but it is a customization of it, so that you don't use numbers until you have to use numbers. And then with Terry, if you actually look into his frequently asked questions, he talks to somebody from Scientific American, and this is true of Terry. Any question that you think you might have that seems hard, you can ask him. He comes up with an answer. And I'm just going to say, I have been playing. See, look, so somebody was asking me, why are you working on the break-even point of this formalism? Because I said the formalism needs Terry, and I want to take Terry's brilliance out of the system so that anybody can, with the book, just achieve the same results, and not rely on Terry saying, "Oh, sure, let's have some break right now, you and I." But you know, it's him. So it says, this is not to advocate dispensing with complex number per se. Okay, surprisingly enough, last August, we wrote a paper together in which he was showing us how you can just completely do what you normally do in quantum mechanics, but without complex numbers. Well, some parts of that, before he understood it completely, surprised him too. So he says, you do not need complex numbers, but then you would need twice the amount of qubits. So he says, I bet if you ask your average working quantum mechanic to come up with a feature that I cannot also demonstrate using only real number entry quantum states, they will fail. And then where's the proof? He says, I've been playing this game a long time and I've been winning. But we're not Terry, so we can't say, sure, ask us. Terry says that you can always find an answer. No, you can't, because you have to be sort of really as knowledgeable as he is, and that's difficult. So you read these questions and you find a lot of meaningful comments about how this system, well, he's funny, let's face it. So I'm going to close down and say, this is my main goal, to show you the diagram. Now the questions were, wait a minute, don't I have more? And yes, you have more. This is the qubit touchdown game that exists because, as I said, Tommy Wong, who got a...
Did you know you can AFK Bloods and Zaya whilst learning to code in Python? Go to boot.dev.
Hello, my name is Tom Wong, and I'm a physics.
This is Tommy Wong, and he got an award in recess when he was in elementary school. He really was good at recess. And so now, when he's a professor, he invented a game to help us learn about quantum computation. So this qubit touchdown really is a bunch of transitions between states using gates. And of course, you roll the dice and you choose a transition based on what's possible and what's not possible. And touchdown means just get on the other side faster than the opponent. You say, well, what exactly can I get this, and where do you get the picture here? And I say that here's a website that you can click. This is the book that I say we need to start reading with reading assignments next week. This book doesn't know about the mystery state formalism, but does, for an absolute beginner, introduce all the methods necessary. Okay, so in second or first lecture, I asked, what is the property of a good book? The conclusion that I forced was it must have a lot of exercises, and I should be able to check my answers. This book has a lot of exercises, and the answers are listed at the end of the book. Then that's a great tool. So the book is free. He updates it if he finds error and so on, because it's free. And then the qubit touchdown here is this, that basically has the ability to, look, these are the cards if you want to play it at home, print it and glue it and so on. And clearly these are all gates. Look, this is the Hadamard gate, and it tells you what it does. And then there's a game board PDF, which is the one I put into the class notes. Now I wonder if you guys can see this diagram in this picture. And the answer should be, well, from 0 to 1, I should go with X. There you go. But you can go from 0 to 1 with more than just X. But let's just put it on the X, which was in our diagram. So this, the diagram from cubic touchdown, is a far more extensive set of transitions that includes the little thing that we want to demonstrate today. What about Z? Z is supposed to go between plus and minus. Look, there is a Z over here that says you could also go from plus to minus. How about H? Well, H was supposed to go from 0 to plus. And notice that sometimes you have an arrow, sometimes you don't have an arrow. So H goes from 0 to plus and plus to 0. And then H goes from minus and 1 and 1 to minus. So H with Z, and then H again and X. This is the diagram. This one here is the diagram that I showed you. See? This one is the diagram that I showed you. And everything else, more transitions, more things for us to prove. All right. So what I said, now I'm going to switch to the other thing so I can write for you. I could say maybe, are there any questions, anything that I'm supposed to, any confusion that I want to eliminate or so on? Yeah, well, I do have to say two things before we get started, absolutely. I'm gonna say here that I told you that people are working even though they don't come to actually to plus. So participant 6, that's good. We have 6 people, that's what I thought. And I'm gonna go to students. Right, so these are the 3 graduate students. Then I have 10 undergraduates. Some of them have dropped, but then I have a new one. I don't have you here, but I will add you. And then I think otherwise I have all the pictures. So if you go 4, 6, 8, 12, but then some are out. And then the high school teachers, they'll help me with the focus group on the faculty learning community for the quantum information science for high school teachers in Indiana. So if I want to go to Ms. Snyder, who came to my workshop in CC, she's in Georgia, and if I click on the picture, then I will go into the GitHub. So if I say, let me see, what's my, let's see if I can go in, but I think it's going to be very easy if it prompts me. It could, see, because I've done this every day this week. So proof that people are actually following and working, even though they can't come to the lecture in the morning. So I click on week 1, and this is a notebook that she submitted. And I didn't ask her for permission, but that's again ask for. I apologize later if necessary. What I'm saying is that she has a very interesting thing over here. For some reason, her matplotlib did not work out, and what we have here is a different structure that shows that, but not the way we did it, but it looks good, right? But it's the matplotlib part didn't work. That's really important. You should make it work because there are some definite meaningful things out of that. So what am I going to do to help her? Okay, we can keep emailing each other and I can propose some things, or I could actually upload something in her GitHub, which shows how to work. But I'm going to meet with everybody, and that's good for you because you are new, totally new. So I'm going to meet with everybody on a weekly basis. And if you are a student in this class and you get a grade, then your grade is an average of 6 meetings that we have. And when are we going to have the meetings? They should be between Friday of a week and say Tuesday of next week. What are we talking about? It's going to be very informal. And it's just, do we know what the week before was about? And can you just name it, state very briefly? Like if I were to run into you on the elevator, no more than 2 minutes, or in the bus stop and the bus is coming, could you quickly put together a sentence or two describing what the week was about in such a way that I say, I think you know what it is. And if not, I can help you. So these meetings are not, this will be an exam, aha, I caught you, don't know, I give you 0 or 50 points or whatever. No, I want to give you 100 points. I want to give you full credit. And so we come to these meetings so that we can either see how much you know already, or I get to explain a little bit more. The meetings are 20 minutes long. I click on 19. This is the schedule as of right now. So I put Ashish over here because I didn't know if you, but I did approve that. Last night I couldn't approve it, but this morning it did show up. I have a bunch of people who haven't yet decided when. I think that Ms. Gelhausen will see you today at 2, unless something changes. And then I have other people with dates, right? So I meet with Ms. Snyder. I go Sunday, 10 o'clock in the morning. And that's when I will get a chance to explain what was it that shift page? What was it that maybe the matplotlib didn't do very well? Now, today, before we get started, I want to write the formalism, I'm going to explain everything, but let's just go into Google Colab. And sorry, I'm at Google Colab. So what is this first week about? Well, it is about the kind of stuff that we're going to discuss. But we are not going to just discuss things by writing them on the board. We are also going to write programs. So if you get a problem about probabilities, because you have to consider the fact that quantum computation is quantum mechanics is entirely probabilistic, then you have to become familiar with the topic and the ideas. And I'm going to create a new notebook. And you can do this by writing down stuff, or you can write a program that simulates, or you can write a program that actually calculates, counts, and then it gives you the same thing that you would have done if you had written things down. So I'm going to go here and under what's new, and I'm going to say that at the very beginning, I said, how about we take a look at this? Nobody really, honestly, genuinely wants you to understand this now. But the fact that it is possible in the environment where we're going to do Qiskit as well as simple probabilities and solve Python, that's important. That's not Mathematica. Mathematica is more powerful than this. But this is also extremely useful. So could you come up with a circuit that is rendered properly? Of course, I put the notebook for I said the notebook is right here. It's my notebook from 3 days ago. So what am I complaining here? I'm complaining about the fact that my circuit looks with colors, but the one that I showed you doesn't. So they're both equally good. But if we said, but we also want colors, then I guess, why don't you make your notebook do this? Because if you do, then you'll have the matplotlib. So I'm very quickly going to show you, as part of week 1, I want to test things out so I know my environment is okay. Then as I move on to other things, I'm going to do very specific things. But first, I just want to see that it's working. So I click on this link, which will take me to the code. Very good. Actually, I don't want this at all. So I'm going to come over here and I'll say the very simple thing that happens over here is that they have short programs that produce the sphere of yesterday. So I don't have time, right? So I'm going to go in here, I'm going to take this and I say, if this works, it should work right away. Let me go and show you. I lost it, right? I'm so random in clicking with the mouse for some reason in this in here. Reset. Let's go to this guy. So I'm going to do this, and you should do it too. But will it work? Doesn't seem to be working. I mean, first it tries, and maybe it will work. And if it does, good for us. And if it doesn't, what's wrong? It says that I don't know what QTIP is, so I can start researching that because they basically have closed this. Some explanation over here. But from what we discussed a while ago, right? I could just say, give me a new code, and it's right here. Move it up at the very top and install it. You have a package, you don't know what it is. Maybe you can research. Now you know what it is. You still don't have it. Go ahead and install it. And you will do something like pip install this. And then you run it, and it comes up with some output, which you can hide. You cannot delete anymore, but hide. And once this is installed, then the actual sphere will show up. That's great because it's what we showed you yesterday in Mathematica. So if you are a student at IU, you get for free Mathematica. If you are not a student at IU, but you're affiliated with IU, there's still a possibility. And if you don't, maybe your institution has it. And if not, then you use Wolfram Alpha. So I'm going to close this and I'm going to say hide output. And then I come back over here. What didn't work before is actually going to produce the sphere now. See? And you see what happens over here, that I have a vector that's completely random. So if I run this again, this is a vector in a different position. Random position. Any arrow in here is a qubit. So randomly pick some arrow. This is very close to 0. So if you were to measure it in the 0-1 basis, very likely you're going to get a 0, but you're going to get a 1, which is much smaller probability. I'm going to run this again from here. All right. With the reason, this is another random insight. Good. We have the same tool, except there's, I guess, you can move it, rotate it, and you cannot do this here. At least not in this notebook, and at least not with this code. So when it comes to some parts didn't work, the thing is why? Well, let's see if we can get something else of the same kind work. So I gave you this not because you can understand the code or you should understand the code, but the output is really good. and it uses matplotlib. And if this works, then the other thing should work. And who knows what happened? Maybe some typo. I said if you are interested in matplotlib, you should go and visit the tutorials or the examples. So I have a hat graph right here, and this is matplotlib from a list of examples and tutorials. Now this is a little bit longer, right? But if I copy all of this, again, my goal is to show you that my environment is ready for anything I might want. I'm going to copy this. All right, if it isn't, then I have to work on that and make sure that it is. And our meetings could discuss that. Well, see, I learned this doesn't work. Show me that. How do I do it? So when I run, you get this, which is a visualization of some data, but doesn't look bad. So if you say, well, I'm not sure exactly what the hat graph is, but then there are lots of tutorials that you can see over here. All you have to do is, I like this one, click, get the code, run it, then I understand. I believe that my notebook is matplotlib ready. And that concludes my background information. So now I'm going to say enough with this, and I'm going to stop sharing. Where's the thing? I gotta do escape and then stop sharing, like so. And now I'm gonna share from the iPad because I'm gonna start writing some things. So I'm gonna say share content. I don't have audio on the iPad, but hopefully that's the microphone out here, and like you can hear me in the same exact way. So when I say show the screen, I'm going to say start broadcasting, and hopefully I'll see here the screen that I have on the iPad. Very good. And I'm going to close this and get this going. And I'm just going to, do I have an eraser somewhere? Where's my eraser? Maybe here. Okay. So actually, I don't know how to erase here, so I'm going to go with what? I'm going to erase like this. But the kind of strange, I'm sorry. In Portland, I use PowerPoint, but I had a free trial, and I could get something from the school, I think, and I will. But at this point, I thought because my trial is expired, I don't have any PowerPoint anymore. So I said, "Oh, but they use freeform, which I haven't used before," and then hey, I'm getting in there. So like I will give you more papers and more stuff that you can. So this story I'm kind of erasing. There should be a way for me in freeform to actually highlight everything and then say you go away.
So it's we control A. Increase the size. What
do you want to do?
You can increase the size of the eraser.
The size, where is that?
Where's the eraser? Just click on it.
Right, this one. I click. See nothing. So eraser. Now I can't keep an erase. Oh,
Yeah,
pick an eraser. Hang on.
I think it's just low.
That is possible. Come on, pick an eraser. I want to pick an eraser. Okay, meanwhile, I'm going to get there in a second. I'm going to start writing and so on. So I'm not very familiar with this freeform. Apparently, it's an infinite canvas. All right, I get this one. Much bigger eraser. Thank you so much. So sorry, I might be able to do things fluently. Yeah. Okay. Now I'm going to pick this guy. Or this guy, which one do I want to do? Apparently so. I would like to write, but I don't want to write with the eraser anymore. So what about this one? I'm going to choose this one. Can I? Oh, that's good, right? Back to the eraser. Can I come back here and I'm going to say, do you think this is going to be too big? We do not know, but let's try. So I'm going to talk about the X gate, and I'm going to talk about the H gate, and also the Z gate. And so in the very beginning, I need you to know that the way we define these gates is by axiom. You are going to say, but I read that every gate is a matrix. True. You know what I'm doing right now? I am postulating the columns of that matrix, but you don't know yet, and you don't need to know. So I'm going to say there are two possibilities. Maybe I'm going to give it a white ball, and then the result is going to be a black ball. But this is by fiat. That's the way it is. if you put a white ball into an X gate, or you to the left or to the top, then out comes on the other side black. It changed the color. And there are only two colors, white and black. You say, what does that correspond to? 0 and 1. So are we talking about the computational basis and ignoring plus, minus, and the other two? The third one, yes. Fine, then what else can you tell me about the X gate? I am going to tell you that if I put a black ball in it, I get a white ball. Fine, that concludes our knowledge about the X gate. All right, let's see what else we're going to discuss. I guess let's talk about H. And you say, I bet you're going to define the Hadamard gate in the exact same way. You are going to tell me what happens when you feed a white ball and a black ball. And then that's going to be the behavior of the Hadamard gate. The answer is yes. But in addition to these axioms, I have to give you rules of combination. Okay, so we will give you those too. Because these axioms are fundamental. Without them, we cannot compute anything. But then if I don't know how to compute the sequence of transformations, then I am stuck. So what he has is a misty state. It's like a little cloud with two outcomes. And in papers, we write them like this. I'm going to tell you that this is essentially a set of outcomes. So when you're looking at this, and you read from the little cubitzer, which is the booklet that I have for the workshop that I had in CC, that's based on a tutorial that we had elsewhere. This one says, if you apply H to white, you get something that is called superposition, that if you were to measure, would give you one of these two outcomes. So the set simply says, I don't know what this is, but if you were to measure, you get either one or the other. The outcomes of what you might get when you measure are inside the curly braces. So this is basically like a set. It's like a set of outcomes. You're going to say, well, what's the probability of getting white? What's the probability of getting black? And so I would say to you, what do you think? And you could say, well, there's a white and a black. There's nothing else. They probably are equally likely. And the answer is, yes, they are equally likely. But if you were to doubt that, there is a rule that you could use to calculate the probability that comes out exactly half. So that's also in the book, Q's for Quantum. And I also use it in the very beginning in the booklet. So you could just say this. Intuitively, I say that if you apply H to white, you get something that gives the potential of either black or white when you measure it. Don't measure it, but that's what it gives you. And if you are going to apply H to the black, again, these are definitions. You cannot negotiate them. The definitions really are giving you the columns of the matrix for H. And you don't know this yet, but you will know that very well by the fourth or fifth week. Now I'm going to say, when I get a black ball and we feed it into the Hadamard gate, I get also two outcomes. The first outcome is a white ball, and then the second outcome is going to be a black ball with a face on it. Now, again, when you measure, that's what John showed us yesterday, you can't, through measurement, you cannot get the face. It's black or white. However, the state itself includes the face. So frequently we are going to say, could you please write down the mathematical notation for this, just so that people who do quantum mechanics normally would say, oh, I know what you're talking about, right? And for you, let's say we expect you to, let's say you know nothing, and therefore in the end you will know most of it, but I'll tell you up front what it should be. So this is supposed to be the answer, 1. And we discussed that this notation is a standard notation that we want to get away from in the very beginning. This is a vector. So I'm going to say that this is a 0, 1. Okay, I don't know if you want me to keep stay consistent with this. That's just notation, which we should keep in mind. And because I have an eraser, I'm going to wipe it out. Because I mean, it's in the video anyway, but I could also leave it there. So what about this? This is going to be 0. And this is going to be 1, 0, like so. So that's the vector and the Dirac notation. Again, I'm going to erase this, because I don't care about it, now at least. And if anybody's asking, I could tell them, but right now I'm just approaching it as like I'm here in front of a group of 6-year-olds, which are very smart, but don't know anything. So smart but ignorant. And then I'm trying to talk to them in a completely self-contained way. And then they say, but you are depriving them of knowing precisely what the math is. Yeah, but we'll get there for sure. That's the whole point. But by the time you are fluent in this, you will have learned the math without knowing. That's my theory. So we will prove it. Now, if I get over here, I'm going to say that this is really one, okay, no, that's the eraser. 1 over square root of 2, and then I say 1, 1, which I can write the way I said in the very beginning. Okay, then you say, oh, that's a vector representation of that state. I agree with you. And okay. Back to this, I'm going to say, well, what's the direct notation of this? It's going to be 1 over square root of 2, 0 plus 1 over square root of 2, 1. And so eraser. Okay, well, all right, it's too big now. So 1 over square root of 2, 1. Now, you could calculate here and say, replace 0 with 1, 0, and replace 1 with 0, 1, then you realize I get the vector notation of that. So all the things that we are writing, I just immediately exactly the math, except we don't want to use the math. We just don't want to use the math. So wipe this out. I showed it to you, it's correct. But let's just not keep carrying it around. We can flash it, flash periodically what it is, and then later on actually learn it. So I come back to this and I'm going to say, what is the formula for this one? Well, it's going to be 1 over square root of 2. But then this one is 1 here and negative 1 over here. That's the face, just a minus. It's a minus that shows up in one of the coefficients. And then I'm going to write this down, and I'm going to also write something next to those numbers so that, because I wanted to say, and then I erased before I got to do that. So 1 over square root 2 times 0 plus, there's no plus, there's a minus. And then I have minus 1 over square root 2 of 1 times 1. So what I would like is to describe what these are. What do you think we call these numbers? Clearly, they are not the probabilities, because the probabilities are supposed to be half. And these are not half, they're the square root of the probability. So they are called probability amplitudes. Okay, probability amplitudes. And what I know is that the probability amplitudes in modulus squared summed up give me a 1. Okay, so there is a difference between what I have in my notation and how the probabilities are calculated, but the probabilities eventually, they're still probabilities. So I'm going to come back over here and I'm going to say, let me erase this also. My goal is to prove that diagram. And when I am done proving it, you have to say, fine, I was believing you, I believed you from the beginning, but that's not about me convincing you that the thing is right. It's about you and I and everybody getting practice, getting things done properly. Right now, I'm introducing the axioms. The thing is, that's only half of the picture. I also have to give you the rules of the game. So I'm going to come back over here and I'm going to say the last gate that we have to introduce at the very beginning is Z. Z applied to white is going to leave it unchanged. So the Z gate is going to change the phase. We never talked about phase, right? Yet, I mean. So here's this. You put a white ball into a Z gate. I don't think the book has a Z gate, by the way. And I'm getting out white. But if I'm getting the useful quantum, I don't think it uses a Z gate. But if you put a black in here, the answer is going to be black with a phase. So now let's discuss, how should we mark phase? I put a phase on top. Could I possibly put a minus thing? Yeah, sure. He does that, and I'm okay with that too. And so should you. So these are the axioms for the 3 gates. This is one gate. This is another gate, and then there's a third gate. So what this shows us is essentially first how a gate works, and then superposition, and then phase.
Wait, does the phase change in the second Hadamard black ball? You have drawn a line on top of the black ball.
Yeah.
The fourth line.
Yes.
There's a phase change for the black ball.
Yeah.
And
Yeah,
then
that's what he shows you in the video.
there's
There's
no phase change for the white ball in the third one.
Third one, no. No, but this is the second person that is asking that. So I don't know exactly why you would think that's the case, but somebody else also asked the same question. The question, I think, if I understand it correctly.
Yeah.
Why is on the first one here, I don't know how to.
I think it's just by symmetry because we would expect that if the white one should.
That's what you're asking. Why isn't there a phase over there?
Yeah.
Okay, but the thing is, it's not definitions. That's how they work. You could say, but explain to me. Oh, I can say something that would then discontinue the conversation, not on purpose. I could say, for example, according to that, I need this. Any gate in quantum computation is any circuit is reversible. And so that means that they are represented by some matrices which are called unitary because they are their own inverse, so to speak. So if I apply H of white, I need to get white. Well, at least that's clear from the video.
Yeah.
And if I apply H to H of black without looking, if I look, I'm done. Then I get black. Well, these are the definitions. If you were to say put a phase on the first white ball for H, it will break it.
Okay.
It will just break it.
Yeah.
These are definitions. So these are definitions. All of them are definitions. These are definitions. These are how the
And I guess the reason we're defining it these ways is because the physics works out like that.
that's right. There's no reason. It's just that what the world does, right? That there's no reason. You say, well, how is nature like that? Well, I don't care. That's the way it is in some sense. And so the reason is much harder. How you might not be able to ever find the reason why nature is like that. Okay. So don't ask, please. Just move on and be successful using it. But you're right. That's how nature is. Therefore, I'm not going to change the definitions because that's what they are. Okay. So I'm gonna come back here and I'm gonna erase some things, but you're the second person that asked that. So I think in the meetings, I need to talk to you guys to see what made you think that there might be or that we could.
Just symmetry, as you said.
Symmetry, but what does that
You
even
do
mean?
it on the black one, so why you cannot do it on the white?
Except this symmetry that you are looking for is gonna break what we need. This is the symmetry that I want. This is the symmetry that I want right here. Where is the thing? See, that's the symmetry that I like. You break this symmetry because of that simple symmetry. So the question is, which symmetry is more valuable? The real one. See what I'm saying? You say symmetry. Okay. So you think that putting a minus here for symmetry, that's the way to do. But I like this symmetry here, but more than the other one.
But why would having a symmetry would then break that one? Like if you get a conjugate on top of,
If I put right here, if I put a phase over here, it just breaks this one here.
why would it break that?
Or you can calculate and you'll see. So once again, I told you there must be a matrix that has a certain property. You put the minus in there, you broke that matrix.
Okay.
You can't break that matrix. I mean, that guy went to Helgoland to put that together for the first time in the world. And now we are disrespected. It looks more symmetric to us. Well, tough, because we didn't invent anything. So I'm gonna say this symmetry. What you think might be symmetry might just not have any real. No, why am I doing this huge thing? So I have
You can also just undo, like you can. press
correct, I have, yeah. All right, so now, these are definitions, but once again, you cannot use these definitions 100% unless you have some rules. So let's describe what the rules are. I'm going to go with eraser and get this. Yeah, I'm sure there's an undo and thank you, and I'm gonna practice. Now let me describe rules. I don't know how to say, maybe rules of engagement. Rules of engagement. Okay. So suppose that you have X or H or Z or something, how about I call it A? And I apply A to a sequence of outcomes, like it could be in state 1, it could be in state 2, it could be in state, I don't know, N, right? So if I have a superposition of states, like I have one already with white, black, or white, negative, black. The what we call linearity basically says you should consider the superposition of the transformation of every single state. This is a rule of engagement. So this is how they work in general. So you have the axioms plus this, and now you're good. Yeah, well, it's died. So back to this, I'm gonna say this is lowercase s2, and then I have that lowercase, I mean a of Sn, and I'm telling you that until I find where undo is, I'm going to say this is Sn. All right, so Shivam, do you think you understand this rule?
SN is a qubit, right?
It's a state, yeah. No, like for example, this would be, this one here would be this guy. Okay, come on. This one would be S1.
Yeah, got it.
And then
Also, I
some-
understood why there's only like a phase thing on top of the black one, because like if you go back to the circular diagram, when we look at negative, the negative is in the minus y direction and positive x.
That is a very hard question, okay? And you keep wanting to know why the axioms are the way they are. And that's a very difficult question. And what I can do is I can encourage you to keep thinking about it, but I will not be able to vet your theory right now. For fear of saying, of missing something, and then you leave happy, but not knowing what you just decided on. So I think keep thinking about it. In fact, in the book, he says, I just explained this to my nephew, and he realized it's a mystery. We need to understand this mystery, but it might take more than a weekend. So you got S1 and S2, but my question is, do you understand the rule of transformation? Is that A applied to a superposition is going to be a superposition of A applied to each one of those. So here's what we had originally. I have 0. I'm going to do this. 0 commutes with 1 using X. And there's an H over here for these guys to commute with plus and minus. And what I would like you to do is to get into the habit of being able to prove properties between these things. Now, when people come to you and you say, prove this to me, you took that class C290 and so on, they will give it to you in this notation. But you have to start saying, you know, the truth is that this here is white ball. And then I have this, and I'm going to take this out. So what I have on that side is basically the black ball. So you have to convert in your misty states. And so you say, give me the question in my misty state formalism, then I will do everything. And maybe we can convert back at the end. The plus that I have over here, which is right here, should be, as we discussed, white followed by black. And then I have this one over here that says, when I look at minus, and so I mean, why don't we write this over here? This is in fact plus. And I think I wrote in the very beginning, let me keep this here. And then this is, okay, so it's very tempting to find out why is that minus there? And I say, keep thinking and read and so on. And if you have a conclusion, make a write a paper, short paper. I'll tell you, there is a, there is a conference in September and they have almost everything they need except posters. So I'm going to tell you that conference still accepts posters until July 4th or 5th. And if anybody wants to put together a poster, I'll show you how. And then conference in Montreal, and you're just there with people that do the same thing, quantum education. So in this case, if you come up with an idea as to why it has to be, then you can just explain to them. So I'm coming over here and I'm going to say, do you realize that this one here takes care of the first transition in this way? It's just an axiom, correct? Then this one over here is going to take care of this part. So two arrows on left and right are basically the same thing as the line without arrows. And I just proved that because that's just it's just the definition. So I'm going to come back over here and I'm going to say, I hope you understand that this line means that the arrows are in both directions. And with that, and so it's the good thing about this. I thought the good thing is that I can move this up somewhere. How can I move it? There you go. I can move it like this. But for now, let me bring it back. So I have infinite space, left, right, up, down, and so on. That's okay. We're not going to run out of space. I got the X spot. I hope you understand that I'm going to say whatever I do already, let me mark it as red. I've done the red thing. No. Nah, that's the undo. Sorry. But see, when you finally need it, you find it. Thank you for telling me anyway. So this is easy. So you could say, how did you solve those? I say through this. These axioms with red took care of that line. Okay, now let's say Shiva, which line would you like me to prove next? And let's pretend. Okay. Yeah, can I move this up? Yeah. let's pretend that you would like me to, okay, I can also make it like this. That's not bad. Then I get more stuff and you can still see what you did before. So I'm going to prove this one here, just a second, black, I want black. I'm gonna prove this one. Do you think I can prove that one? Is it easy or hard?
Which one?
The arrow that I just drew.
I can't. Oh, okay, yeah.
Of course, that's just the definition.
Yeah, that's
So, sorry, don't, yeah, okay, but how about this other one? And the answer is, I don't know how to do h of white. So how about we apply the transformation rules? And I'm gonna say h of white is equal to black, white, black. But that's the rule, and I don't discuss this. Well, so I would like to do h of black, white, I'm sorry. That's gonna be h applied to, and guess what that was? It's gonna be white with black. Did we introduce a rule that describes how we should behave here? What do you think, Emma?
I mean, you can use the combination.
Exactly, that's the combination. So I'm gonna say, please use the superposition of h applied to white, comma, h applied to black. So in other words, I still have two outcomes. These are the two outcomes that I have. Well, what is h of white? That's going to be white, black. And then I have over here white, followed by black with a phase on top. Okay, we should describe something like this here. If I have, I don't know, state one, okay. So if I have state one, state two, blah, 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 state n, and then I have some more, like for example, T1, T2, so to speak, all the way to Tm, I guess, Tn, M, I don't know how many outcomes I have. Then this is the same thing as S1, S2, Sn, T1, T2, Tm, Tm. So I'm going to erase this, but the idea is that if I have the angle curly braces inside curly braces, they act as a set union. So I'm going to say that this here is like the set union,
which is OR.
Of just set union. But you're right, that's in some sense in logic like that, of outcomes. And then here's what happens now. So this is set union of outcomes. I'm going to write them down as follows. I'll put this here. So I will have this outcome and then this outcome, followed by the outcome that I have in the other one, followed by this outcome, which now has a phase on it. And so for the first time ever, I'm going to experience interference. This interference is going to be destructive. So the net result here is going to be that these guys here are going to cancel each other, just like 3 and minus 3. I'm going to say this is called destructive interference. And what you get is white, white. So now the question is, can I simplify this further? Well, this says that I have two possible outcomes, white or white, with equal probability. Well, that means that I only have white. So I'm going to come back and I'm going to put this here. But by abuse of language, you're going to say a set of only one outcome is that outcome. So I just proved that this, in fact, produces the white ball. Right? So the white ball really is one side of the coin. It's a classical value, but 0 as a qubit only has one component and kind of really approximates that, just that value. Even though it's still a qubit, really approximates the classical value. As a result, instead of writing curly braces or a misty state with just one ball inside, just put the ball. So this concludes our proof of this guy. Actually, I'm gonna choose this one so I can do erasing like so. And I'm just gonna come with blue now, and I'm gonna say that this blue is going to be based on this blue. The blue that you have there is because of this as well as this.
But you have written the net outcomes, the second one.
This one?
And on the right hand side, yes.
Set. I'm sorry for my
Set.
set union of outcomes.
Set union.
I'm so sorry. I will try to be more I make my writing more legible. So I just proved half of this diagram. The other half is not much harder, but it exposes you to how we calculate. Now, what should you do? You should look over the first few pages in the QBitSer because I am explaining exactly these things. The book in the beginning is not written like a book. It's like a dialogue in which we just highlight the things. There's a lot that's not said that's in what they think when they say there are two people. A little bit later, it turns to prose and so on. So with this, I guess I introduced superposition as a set of outcomes, and then one rule of linearity. I also introduced phase, and I said that if you have a set inside a set, you should just take the union of those two outcomes. If you see outcomes that have different phase, they cancel each other. And I proved. Now I would go to Shivam and I'm going to say, Shivam, if I were to put a minus, for the fun of it, on the first white, then we are gonna get nothing altogether. And it's not possible to just disappear the whole input, right? So that's why, so that rule doesn't work. Now you could say, but maybe I can invent something else. That's quite true, and that's why I keep thinking. Maybe you can explain what's happening, or maybe you can come up with new things. So in March, we had a talk by an unbelievable speaker, currently working in Colorado. She is developing new materials. Now, honestly, the goal is to create superconducting materials at room temperature, which is very hard. You never. But what she's doing, she's putting electrons in the right place with a microscope to get a new material altogether. And so she did say a couple of, this conducts a little bit better, this conducts even better, this doesn't conduct well. So is that what you're doing? I guess so. But it's tough. And if I say it from the beginning, people will laugh at me because it's really a difficult problem. So you should continue to think, if you want, and invent your own thing that may or may not be useful, but at least it's an exercise that's meaningful. For this is the end of our first week, and so for what should you do, I think you should read, I will email you, but you should read the beginning of the few pages, like 5-10 pages in the qubit set, and see if you can work this out, this diagram completely, and you are comfortable with it. So next week we are going to, there's a plan as to what we are going to do in terms of actual formalisms. We are really going to look into linear algebra and matrices next week just to see how it looks. Period. But we're also going to go look into system of 2 qubits and slowly look into entanglement. A system of 2 qubits is not an outcome of a set of 2 outcomes. So then that's explained in the qubit set booklet. But again, you can ask questions, or you can wait until Monday when I'm going to introduce those. So hopefully this was not prohibitively difficult. We have some axioms that define the gates, and we have some rules that apply over all gates. And we proved half of this diagram. So hopefully that's acceptable, and I look forward to meet with you between now and Tuesday or whenever you have time. So that's the end of this. I'm going to stop sharing and see if I can do that. Where are you, Zoom? Already, maybe? Yeah, stop sharing. And this is us. And now I'm going to say, participants, I have, okay. Yeah, we lost, I don't know who, I lost Ahmad maybe, but that's okay, he's busy. So, any questions before we discontinue? Stop and leave. Any questions from people online or from people in here in this room? If not, thank you for your patience. I'm going to have this recording posted in about an hour. And then I'm going to bug you, all of you, to come to Zoom to talk briefly, 20 minutes about the week. Thank you so much again.
Thank you.
I'm going to leave from the iPad.
So Professor, are we primarily going to be coding it using Qiskit, like
Yeah, as far as coding is concerned, you can also do Mathematica, but as far as coding is concerned, that's what we do. Notebook, so I have to catch you up.
Yeah.
So we are living in a Colab notebook, and we do Python. We can do Python because I have a probability problem.
Yeah.
And I either don't know how to do it. If I know how to do it, I can write LaTeX in the note. That's also good.
Yeah.
Really nice mathematics. Or I can write programs that would produce what I would otherwise do if I were to throw the dice a million times. So that's classical stuff. And then as far as the coding, it's going to be Qiskit.
Yeah, sure. That's fine.
So since you're so new, I have to show you where the textbooks are for this.
Oh, yeah.
See?
Also, I got access to resources tab.
Because I took you out because you dropped.
Yeah.
I came in and so I have to add you now. See you
Thank
later.
you.
Have a good weekend.
Have a good weekend.
Yeah.
I
So
thought,
Ashish,
I
right?
thought that happened automatically, like.
Well, some things happen automatically. For example, wouldn't you expect the e-ad to happen automatically? Didn't. I had to go in and.
No, like for instance, I get automatically added to the canvas.
That's
code.
true, some things, as I said. So let me show you, share, this is for Ashish. So if I go back into. To Archive H, I go in here. I go click on class notes, and then I click on syllabus. This is describing the class. So what do I want from you? What I want you is to understand these 6 cases of quantum advantage. This is why using quantum gates and writing quantum programs would be better with respect to classical computing. So there are some areas in which we beat that type of computing. So then, if at the end of this class you understand what these mean, and you can write the circuits, and you can argue if people were to say, "Oh, but explain them to me," then we're good. And so I scroll down. So we don't do the CHSH, which you said you implemented, but they implemented it for us yesterday in Mathematica. So I need to show you what all these things are. We do GAZ. The reason being, I don't want to get into doing stuff, repeating until I get an 85%. I want to show you that all possible paths lead to winning. This is the textbook that I wrote for a workshop in CC in March. And so this is what I said you should be reading. Superposition, I guess, phase, 1-qubit Gacy. So your question is about Qiskit. So if you scroll through this, you will find that the first example of a circuit is in Qiskit. And that was the answer, see? Right here, see?
Yeah.
And that's all we want. I mean, because otherwise it would be too much. So one other goal that we have is, could we possibly present this material in such a way that people could take that material and go to high school, incoming students in high school? Could they understand it this way? So hopefully, yes, but we'll have to prove it. And I guess if you scroll down and say, that's the Qs for quantum, I gave you a hard copy. This is the little booklet, like 80 pages or so. This is really what they do in Waterloo. This is the mathematics for young students. And so this doesn't cut any corners, but it's just the math. But it's so well put together, lots of exercises. There's 4 chapters. Some introduction, complex numbers, linear algebra, which matrices, and then quantum mechanics. So out of this, I made a homework with 4 different parts. I added probabilities, and we discussed this week probability. So now finally, the last one is the book that we mentioned. This is a free book. Again, this is all math. It says, let's suppose you don't know anything. The first thing you should know is classical computation. So it introduces and not, and so on. And from that it says, okay, now you understand gates. Okay, there are some quantum gates. And slowly introduces. So this has lots of exercise, very, very well explained. Like assumes you know nothing. And then exercises are answered at the end. So you can check your work, which is really fundamental.
So this is the one you recommend to follow.
That's the actual textbook, but we do the Mrs. State formalism first.
Gotcha.
You know, with the bubbles, the thing that I gave. And so I don't want to make it like, oh, we should do much more. I will post like 20 more books, but they are not stuff that you should read unless you want or later. I want you to have resources. But for this class, Tommy Wong's book, Terry Rudolph's book, my booklet, Qiskit in collab, that's it.
Thank you.
Very good. And we'll see you later. So I'm gonna say skip. Okay, but this at least got into the recording. Hey, I need to add you, the picture and so on. I'll do it later.
Well,
this,
so yesterday I went to like I used Portal and like the e-drop and everything.
And I got the email,
So you got it.
but after 10 o'clock in the evening, I can't get access. So in the morning though, I was able and I approved it.
Okay. So I should probably get it soon, right? Because I haven't really received anything on my side.
I
saying
hope
that.
so. He, like I said, he went in, out, in, and so on. His first enrollment instantaneous, okay? Then when he dropped out, that took a while. I was notified that there will be a drop, and 2 days later it showed up. Then he had me approve the e-ad. And then it took a day for him to show up after my approval. I see. So who knows how they work over the weekend, maybe Saturday, if not Monday. But since I do, I don't have you anywhere. But as soon as I have you, basically, this is a script where you can make appointments. Like for example,
And first, you can put me down like for, Monday.
I can. So this is him, because I have him. And now he's yesterday or Wednesday at 2. I can put you as you say.
You can put me down on Monday after this last meeting.
Okay, let me go there. So. I do have some times on Monday that I need to acknowledge, so. Monday at 11:30, Monday at 11, and those are not available. So 12 is under 12:30, I propose
I can do Tuesday, too. Tuesday's fine.
Tuesday at 11.
Yeah, that's great.
Then I'll put you Tuesday at 11, I'll put you now. But Tuesday at 11, and if something changes, whatever will.
Yeah. Sure. All right, thank you, brother. I think that should like basic understanding of everything you guys did this week, but I'll go through it this weekend.
Yeah, and that first meeting, we could just discuss that.
Yeah, sure.
No problem. All righty. Not this, but this. I'll change the colors backwards. Like so. And then I put for the board program, I'm gonna put red. Okay, so when I apply, and then if I go on the on Monday, it says Monday at 11, so I'm gonna go. C219. That's gonna go on. So. When I open the lectures for 0619. And I go to sheet. Make this as big as possible. And so he said Tuesday, so this sounds good. And I'm gonna organize this. Maybe not. Maybe. Then this is June 25. And I have, on Tuesday I have 12:30, he said 11, okay, like that. Yeah. So then I get this guy. Put it in front of this entry. Okay, so now that's 1 more percent, maybe sign up. All right, great. I think that's it. So I'm gonna stop sharing. I think I'm gonna stop sharing. This is the collab that we like to together. This is a scheduling, which by the way, if I reload, something has changed. And this is the class, and then today we worked on this. I introduced some books. We have some new person here that knows stuff, but also needs to catch up a little bit. 28 is because it's a brown, because of Fridays, we have to worry about, weekly meetings. We don't have to happen on Friday, but it happen as Friday to which is Tuesday. But that's what we have to think about it. And then we have. We have this. As a class. And I guess that's it. So I'm gonna stop sharing, and I'm going to, how about I just stop recording? Stop recording. Yes.